Okay, so if you want to do submit corrections for the exam, that's perfectly fine, but you have to come by and see me. So come by and see me. I want to basically have you go up to the board and look through things. And I want to make sure it's really rock solid. So there's that. Then you have another assignment, which I did not give out here, but what is the other assignment? Do the problems you haven't done. And then that we need a time for that. When would be a good time? Hand it in sometime next week. We'll make it big next week. Here is also a homework 6. It's on kind of hydrogen atom stuff. I don't think you'll find it that involved. I think it's fairly straightforward. And then as promised, I said you would be working through the Z component in this little daily homework. So in daily homework 8, you will prove. You will prove that the LZ operator equals minus I H bar partial with respect to phi. Okay? And what you're going to do, you're going to start off with the Z component here. You're going to start with. We know that Z equals R cross P. And how did you find the LZ operator? If I tell you that this is R cross P and say find LZ, just what would you do? Yeah, you'd say, oh, I know this. This is I, J, K. What would you go here? RX, RY, RZ, but we have better ways of writing them now. What are they? XYZ. Use XYZ. And then down here go PX, PY. So how do you get them to get the Z direction then? You cross up this column, you cross up this row, and you look at this little chart, this one here. So this is your XPY minus Y PX. Now, how do you make this an operator? What else? That's on everything. And what does PY have? And then same thing for this guy. So if you put this in the right order, this will become, meaning starting off with a positive thing. This guy I'll leave first because it comes under the positive sign. Then you have this. And you're going to prove that basically this goes to here. And when you do these proofs, you have to let this act on something. So I'm going to let this act on a test function. So if this acts on a test function, maybe this can be any function. So you're going to work on that, and you're going to show that this goes to minus IH bar, partial with respect to phi, acting on that. That's what you're going to do. I kind of lead you how to do it, but I'm going to start off with this. I'm going to start off with, if you look at part A here, I'm going to do one of these things for you. You're going to first prove these 9 identities. You're not going to need all 9, but I want you to. Okay, so I'll do any one of them. You tell me which one you want me to do, and we'll do it. So there's 9 identities here. Pick one, and I'll do one. Don't all jump at once. The center one. The center one. The partial theta with respect to phi. I mean, why? Is that what you mean? Okay. So, hint on daily homework. Let's prove. Now, we're in what kind of coordinate systems are we in? The hydrogen atom? Spherical coordinates. So what do we know about these? We know that remember your Z is R cosine of theta? Remember that? Okay. So your cosine of theta is Z over R. Does that make sense? So if I were to say, find this, and you only have that, what would you do? Good review of calculus. Really good. And you would not take the inverse cosine of this, because usually whenever you're involved with inverse cosine, it means you made a mistake. You just do something messed up. So then what you're gonna do is you're just gonna take the derivative of this with respect to y. So what would be the derivative of cosine theta with respect to y? Try again. Right? Does theta depend on y? What does y depend upon in polar coordinates? Remember, your r is x squared plus y squared plus z squared, like that. But it actually does. So what is the partial of theta with respect to y? No. Chain rule. Minus the sine of theta. Chain rule. Does it here? Chain rule. The partial. Chain rule. Theta with respect to y. Excellent. Good. Okay. Now that count 3 now, right? Explain what I just did. How does it change? Yeah, so if I have some word function here, that's a function of u. Okay. And u is some word function of x. So if I have the partial of f with respect to x, the same thing as partial of f with respect to u, partial of u with respect to x. Right? Yeah, I remember that. Good, excellent, okay. So I'm going to take the partial of cosine of theta with respect to y, which is going to be the same thing as the partial of cosine of theta with respect to theta, partial of theta with respect to y. Right? Which is minus the sine of theta, partial of theta with respect to y. Now I have to take the partial with respect to y of my buddy here. What is that? What do you know about x, y, and z? X, y, and z are all examples of independent variables. So what would be the partial of z with respect to y then? If x, y, and z are independent? 0. So I can take this z out of here, okay? And then take this. So this gives me minus the sine of theta, partial of theta with respect to y. Z, partial with respect to y. So what is that? This is one long exercise in chain. Chain rule. That's right. That's right. -1. Excellent. Good. Now, this is the minus signs go out. Now, if you look on here, hey, what is the, if you look over here on the sheet, you're also going to prove that this partial of r with respect to y is what? Y over r. You're going to prove that right here. Now let's put in what we know about these things. Z is what? Z is r cosine of theta in spherical coordinates. What is y in spherical coordinates? R sine of theta sine of phi. Let me finish this thing. This is all over R cubed. And this is sine of theta. Partial theta with respect to y. Sine of theta is cancel. R here, change the ones here, so this gives me the partial of theta with respect to y, equaling cosine of theta, sine of phi, R, which is exactly what I wanted to prove. Okay. Why? Why does x equal r sine of theta, sine of phi, y equals r sine of theta, sine of phi, this equals r. Prove those for me. This is r. Where in this picture is theta? In physics. It's here. All right, so if I drop this little perpendicular here, as perpendicular, this is my z right here. So what does that z have to equal from this right triangle? Has to be r cosine of theta. Now tell me about this side right here. What is that side? This is r sine of theta. How do you get the x and y coordinates in here? For circle coordinates. Imagine a light shining in here, so this line is going to cast a shadow on this xy plane. And it's here, and this value here is nothing but my r sine of theta. Now where's my phi? Yeah. So it's here, so this is right angle, this is x, and this is y. So if you want this x value here, what is it going to be? It's going to be the hypotenuse here times cosine of phi. Boom. But this side here, which is the opposite, is going to be the hypotenuse times the sine of phi. Okay. What would happen if you look up these equations in a math book? Yeah, you're gonna have a phi here, you're gonna have a theta. Things reflect. Okay. So you're gonna do that, and if you look over here, you get to use another chain rule in a more complicated fashion. So you get a more complicated chain rule. So this is one long exercise. It's actually easy to do. It's just one long exercise in the chain. If you haven't had thermal yet, you'll be grateful for this because it turns out this is all you're doing. You should take thermal, have no clue what to do. Start taking partial derivatives. You're probably gonna be right this one. Okay. Questions? Okay. So there's that. Okay, now with that said, let's go on to multi-electron heavens. Oh, also, I'm on a thesis committee on Friday, so we will not have a class on Friday. So we have some makeup classes to make. The makeup classes I will not hold you responsible for, but I do want to go over the material because we'll probably have to have classes not at the same time. I'll have them all recorded so you can watch the recordings. But anything we have a makeup class for, I will not hold you responsible for because it's not for me. So there's, I think, three makeup classes. One.
Raise my hand.
Yes.
Are we gonna have a third test before the final, or are we gonna?
So what we decided with the third test is it's gonna be basically a roll of a dice. Okay, now it's gonna be the following, is that it's gonna be a take-home third test.
Oh.
You know, you can use your books, you can use your notes, not other people, but you can come by and see me, and I'll give you a push in the things, so, okay? And that'll be coming out hopefully soon. We could do it with dice. Get like some D&D dice and throw them, you're an elf. Did I pass? No. That's what happens when you have Nora. Thank you, that makes sense. Not that it's related to it, but Lego has a really cool Dungeons and Dragons.
I bought that for you, it improves my grade.
Let's go on with this. Okay, so what are we doing? So how do we write? Do we write the Schrodinger equation for a multi-electron atom? So let's draw it. So here's our nucleus. Let's have some charge ZE. We're gonna have an electron over here. I'll say it's that position R1. Here's a little electron. Here's another little electron at R2. I'm just gonna put in 3. 3. You can have as many electrons as you want. It does not matter. Okay, you know exactly how to write the Schrodinger equation. You tell me what to do. Where do you always start? You start with the classical energy expression. Okay, so what would be the classical energy expression? It'd be T plus V. Well, and what would make up T? You'd have 3 kinetic energies coming in here for each of these ones here. So you'd have a 1/2. This is a mass electron. I'll say V1 squared. This is the velocity of the first particle. Plus 1/2 m V2 squared velocity of the second kinetic energy of the second. Plus the same thing. What else would you have? Yeah, what would be the potentials here? You need the total potential energy for that system. And what would it be? You have the kinetic energy between each of these, so there'd be 3 of those terms.
And then between each of them.
And then this one, and then this. Okay. So what do you do? You'd have the kinetic energy. Let's do the ones of the electron and the nucleus first. So you have plus K ZE minus E over R1. And this R1 here would be what? It's really the magnitude of R1. Okay. Plus K ZE minus E over R2 plus K ZE minus E over R3. What else would you have then? How do you now put in the repulsion between the electrons? Plus K minus E minus E. Now what would go in next? What would this value right here be? This is R2 minus R1, and you need the magnitude of that. So this would be over the magnitude of R2 minus R1. Plus, we have K minus E minus E. Now, what about this one here? What would that one be? This is R3 minus R2. So this is over the magnitude of R3 minus R2. And the last one, with my buddy like this. What is that one? That's R2 minus R3, right? I mean R1 minus R3. This plus this equals that. Now what? This is so classical. So how do you do that? Well, I'll put top and bottom here by the mass. So this would become P1 squared over 2m plus P2 squared over 2m plus P3 squared over 2m plus all the V terms. So they go to. This value is what? This value is P1x squared plus P1y squared plus P1z squared. What is that going to become? Put in our little prescription here, and what does this go to when we quantize this? When we quantize this, this is going to go to what? This is going to go to minus h bar squared respect to x1 squared minus h bar squared second derivative y1 squared minus h bar squared second derivative right? And how do you write this? You'd really write this as minus h bar squared. We'll plot in here, and you put a little 1 here, and what would that little 1 refer to? The x1, the y1, and the z1. What's going to happen with this fellow? This fellow, same thing, but 2 and 3. It's going to act on the second coordinate, the third coordinate. So let's write, and then this whole thing has to have an act on psi. So if you do this whole thing here, what are you left with? And when you do this whole thing here, this will go to I h bar partial with respect to t acting on psi here, right? Because that's what this guy does here. Okay, equals. I'll pull out the minus h bar squared over 2m. And have a plottion for the first set of coordinates, second, third. Okay, and then what? All those kinetic energy terms. So minus k z e squared over r1. It's k z. Oh, these are all acting on psi. Just psi here. Minus k z e squared r2 psi minus k z e squared r3. That, and then plus k e squared r1 minus, oh no, the same thing. Not that it matters. Psi. That's k e squared psi r 3 minus 2 plus k e squared psi r 3. There. That would be the exact Schrodinger equation for a 3-electron. How easy do you think that is to solve? It turns out to be utterly pathological to do. And so what you have to do is you actually have to do numerical techniques for this. And so you can take what you're not going to do. Well, what you can do, there's very, very sophisticated techniques you can do. One of them is called Hartree-Fock. And you have to say Fock very carefully because it actually, his last name is Fock. Okay, F-O-C-K. You say it and spell it carefully. Okay. And then you could also maybe do density functional theory. There's a lot of different approximation schemes you can have for this. Okay. I'm going to give you kind of what happens overall. And so this must be solved. I'll give you some examples here. So it's called Hartree-Fock. Density functional theory. This is called DFT. There's a lot of there's other techniques too, but they're two of the big ones. I'm more familiar with Hartree-Fock than with density functional theory. Again, these are really broad techniques that once you know them, you can just start hammering trouble on top of these. But what's the result? Okay, well, something you probably know from chemistry. How does that diagram go from chemistry? You have this chemistry diagram that looks like this: 1s, 2s, 2p. Probably not that at all. 3s, 3p, 3d, 4s, 4p, 4d, 4. What comes after d? F. And you have then 5s, 5p. Now, how does this fill? Let me draw the little arrows like this. That's all the little arrows. Plot energy, and then energy is going to be increasing this way. I'll go in. So in other words, the energy is basically increasing. So give me an atom. Does anyone have periodic table with them? I look up something. Look up which is in. Okay. So we have arsenic, and we have chlorine. Now, don't do something phosphorus like green. Actually, this is the 235. What's chromium? Z equals.
That's the 24.
Okay, so let's do chromium. Z equals 24. Again, the Z is called the what? Z is atomic number, and it is the number of protons. If you have a neutral atom, it's also in the number of electrons. So let's fill this up. So according to this, what happens here? We hit the 1s first. How many electrons can go into 1s? 2. Does that make sense? What are all the quantum numbers for this one? The 1 stands for. And thank you. Okay, what is N called? Principal quantum number. Okay. So the S is L, which S is an L of 0. Okay. And then the 2 is going to be the number of electrons you can put in there. Why couldn't we only put 2 electrons in that state? Spin up, spin down. Okay, so where do they go next? They now go to the 2s here. How many can we put in that S state? 2. Where do they go next, according to the slope prescription? Now they happen over to 2p. P has an L of 1. So how many electrons can go in there? Why 6? Because the L equals 1, how many M states are there? 3. And each of those states can have a spin up or spin down. So this is 6. So we have how many electrons so far? 10, 14 more to go. Okay, according to this, what do we do? 3s. How many in there? 2. Now where? 3p. Okay. What happens with 3p? 6. Now where? Yeah, I guess something odd here. You think probably maybe like finish up all the p's. I mean, all the 3's, but you don't. Goes to a 4s. This is 2. So now we have 20. We have 14 more to go. Now we hop over to the 3d. The D is a L equals 2. So how many electrons can go in there? 10. And we now have 30 electrons. We only have 4 more to go.
I really use 24.
And we're done. Because we're past that. So how many go in there? 4. Right? Because this is 10, 10. Well, here's 10, right? And then here's another 10. So 4 go in here.
5 show in 3D, and then 1 goes in the 4s. At least on this.
Well, okay, that's actually doing it when you go through and do the real calculations. This is just from a general gross Now, what you're gonna find with this is what you do first, but just know you will get fluctuations. Okay, this is kind of a generic scheme for anything. It doesn't mean everything's gonna follow this. In fact, the bigger your Z gets, then you're gonna start getting things that look funky. So you might actually get something like that, because you're putting in effects that are not coming in from these approximation methods.
So, quick question, because I was always curious about this, is it goes from vanadium, which has, 3 in the 3D and then 2 in the 4S.
Right, hang on, you have Nate, is that V?
Yeah.
Okay, and you have how much?
3 in the 3D and
3 in the 3D,
and then 4 in the, or sorry, 2 in 4S.
and 2, then 4S?
So that jumps up to chromium, which the electron switches from the S into the D and.
Okay, so this is vanadium.
Yes.
Now you're saying the chromium effects?
Chromium is, the 3D with 5 in it and then 1 in the 4S. And then it goes to manganese and it adds, that 1 electron back in the 4S. So 3D 5 and 4S.
Okay, there's a couple of things going on here. So first of all, what kind of things can be happening here? Okay. If I had to guess what was happening here, because to be honest, I don't know. Again, just do the scheme, but the thing I'm asking you to do is just do the scheme. We have not accounted for something. What have we not accounted for? Electrons have spin. And what happens here is that if something has spin, there's also a corresponding magnetic field connected. And those spins can actually interact with, so the magnetic fields from these particles here can interact with other magnetic fields, with the mu from with other particles. That's referred to as a spin orbit interaction. And so when you start putting in spin orbit interactions, you start getting, my guess is it's probably a spin orbit interaction. Are you getting stuff like that? But I do not know that for a fact. The other thing that can happen is that these have different shapes here. And depending on the shapes here, you could have, when you start getting these states like this, you start getting what are called crystal field effects. And my guess is probably the ultimate thing that's going on here are crystal field effects. Would be my guess. I don't know. But you can start, that little scheme will break apart. This is kind of a generic, do this first, call this your guess. It's going to work really well when the Z is kind of lower. Once you start getting into the D6 being filled and stuff like that, it can start getting wonky. But do that for the first approximation. Okay, because you can see even to a first approximation, it's not too bad here. Just basically what's happening is, I don't know why it has this one coming in lower, but it is, and then you're having one of them go down here. But it's at least ordinary.
I see a whole bunch of stuff on there.
Yeah, and it's going to be because of all these, primarily it's going to be spin orbit interactions, which are really, really fun. Well, actually, you can put them in. But then these strings get a lot harder. But they're spin orbit interactions. That make sense? Questions? Okay. Speaking of this. So let's take a look. That one's going to be a little too complicated. Let's ask, what happens when there are more than one electron in a shell? In the shell. Now explain what I mean by this. Is in fill. So let's take this example here. I'm going to use this one over here, in this case here. So what's going to happen in this case? So let's take the case where we have, as an example here, 3D4. So if you look at the energy level here, okay, how many D states are there? The D there are 5, right? So this is your, if you look at the M value. This is your 2, 1, 0, minus 1. That's 2. So you go and put in the electrons here, they're going to be something like this. They often feel like this, and then they go back and then they go the other way. The question is, what's going to happen? You get something very odd happening here. Turns out that these spins here, these spin and L values and couple together. I want to show you how this happens. Let's ask how it's spin angular momentum, and spin and angular momentum. Coupled together. So I want to show you how this happens here. I'm going to do it with an example here. Let's say we have 2 electrons in a L equals 1 state. So for L equals 1, we have this 1, 0, minus 1. Question is, what can happen here? So we have the S of 1 particle, and that's the spin of 1 particle. And then we have an S of another particle. We're going to add them together. But then what also happens? The fact that they have an L here means what? It also means we have an we have an orbital angular momentum for 1 particle. And we can add that to the orbital angular momentum of the second particle. The question is, what can happen here? So what can happen here is that if you look at this case here, okay, what do you know about these spins? These spins can be spin up or spin down. So what can happen here is I could have a case like this. I could have this spin coupling to this spin. Or how else could I have it? I could have this spin coupling to that spin. Right? And the same with this over here. I could have this right here. I could have L1 and L2. Or I can have, again, there's going to be a whole bunch of different values here. I can have basically things like this, where this is L1, this is L2. So in a case like this would be my S total. In this case here, this would be my S total. In this case here, this would be my L total. In this case here, this would be my L total. The question is, what are all these possible values? Coupled angular momentum. The spin is nothing but an angular momentum just for a spinning ball. Okay, I'm not going to do the proof because the proof turns out to be really, really hard. It turns out to be you need group theory for this, and that's well beyond the scope of this course. But the result is very, very simple. The result is easy to apply. Here's the result. When 2 angular momentum let's not say L1 and L2. It could just as well be S1 and S2. It could be S1 and L1, any generic angular momentum. So I could have this, this, okay, or I could have this. Any two generic angular momentum, it doesn't matter what I take. When you add together their quantum numbers here, the range on this, you're out for the combination. This is the combination. It's going to be the sum of the two. But then I'm going to keep on subtracting one from this. And so I go all the way down to the absolute value of L1 minus L2. They're all the possible combined L values for this. Let's see what happens in our case over here. In our case, L1 is 1 and L2 is 2. So what is my range on the combined values here? So this is the total angular momentum for this two electron system in the L state. This is just the orbital part. Oh, this is the one. So according to this, it goes from 1 plus 1, so this is a 2. And I keep on subtracting this till I get to the magnitude of the difference. So what's the magnitude of the difference? 0. So I can have a 1 and I can have a 0 here with this. You give these new names. This value here. Let's start over here. Okay, normally what has an L equals 0 state? What kind of orbital? S. This one here you call capital S. It's always a capital. What do you think this one is? Capital P. What do you think the 2 is? Capital D. So that's what the orbital angular momentum is. Well, spin is nothing but angular momentum. Okay. So we have an S1. What is the S1 for electron? Half. Hey, what is an S2 for electron? Try again. What is the S2 for electron? The S values can only be. If you're an electron, you're born with an S of half. That's what you want. Okay. So now, if we look at the combination here, what is this going to be? I could have 1 or 0. Okay. What are the M sub S values? So if I were to say the M sub S 1, 2 values here. 5 of 1, they are 1, 0, minus 1. So there are 3 states. So this is called a triplet state. Because there are 3 of them. Okay. And what this value is, this right here, there's only one of these guys. This is called a simple state. So what you're going to do, is you're going to take an L here. This is L, but this L is not refers to this guy here. You put this here, so this L here is going to be one of these 3 values here. Okay, so this is your combined L value. And up here, you always write this as 2S plus 1. And this right here, this S here, this is your combined S value. So in each of these states here, what could we have? In each of these states here, this state could have either this or this. This state could have either this or this. And this state could have either this or this. Does that make sense? So what could I have? If I had this thing, I could write this as S, and I could have a 3 up here, because if I put a 1 in here, that gives me a 3. So this is the S12 equals 1 state. Or I could have an S0, because this is my S12 equals 0 state. Because you always have to do 2S plus 1, like this. Well, what could I then have for the P? You have capital P or capital P. This one would be a 3. This one would be a 0. What else could I have? I can have my D state as well, when I couple these together. So I'd have a D3, or I could have a D1, I'm putting a 0 here. This should be a 1. I have no idea how I got 0. Oh, because I have 0 there. If you put a 0 here, you get the 1 here. Sorry about that. Okay. Now, orbital angular momentum. Orbital angular momentum is angular momentum. Spin is an angular momentum. What do you think the spin angular momentum and the orbital angular momentum can do? That can couple to make the total angular momentum for the entire system. Note the L and S values can couple to make the total angular momentum J. So let's figure out what to do this. With my L12, I can have either 2, 1, or 0. With my S12, I can have either 0 or 1. How do you think they're going to couple together? This value can couple together with this, or this. And this one can couple together with this, or this. Okay. So let's go and figure out what's going to happen here. So let's do this one here. Let's couple S12 equals 2 and S12 equals 1. So I'll call this J12. Hey, where do you think this is going to go from? The sum to the absolute value of the difference. So if I couple these two together, the maximum value is a 3. Okay, and this is going to go down to, keep on subtracting 1 until you get to the difference of these guys. The difference is going to be 1. You can have 1 in there like this. Okay. These are the J values. Now this is for the L equals 2. This is for the L equals 2 state. Where you put those is over here. You put the J values down here. So in this case here, this could be in a what? This could be in a 3 state, a 2 state, or a 1 state. Now what happens if I have the same thing? I have S12 equaling 0. What are the values here? Okay, try again. J12 can be the sum, which is a 2. You keep on subtracting 1 till you get to the difference. You just have 2. This is this here, so that means that this one here can only be this one here. I remember my friend once. S12 equals 1, and S12 equals 1. What's my range on J12? 2, 1, 0. So I put those over here. So this could be either a 2, a 1, or 0. What about if I have L12 equaling 1, and S12 equaling 0, this can only be a 1. This is a J12 equaling 1, and that means that this one can only be a 1. That's how we can answer. Tell me about my buddy S. Yeah, since this is a 0, this one can only be a 1, and this one can only be a. Okay, this notation, so we're gonna put the J value down here, and you always write it as a capital J. This notation right here is called spectroscopic. Notation. Now notice, how many particles did we couple? 2, and they're just in a low little p state. What happens if you have 3? Well, that'll be what we do next time. Okay. So when you look at real atomic spectra, you basically, you have all these lines and they're all labeled with things like this, and you go, what the hell is going on? Okay, this is what's going on. All these spins coupled, and then what happens is that's when you start getting the interactions between, you're starting to get all those couplings between angular momentum and S. And that's called fine structure splitting or hyperfine splitting. It's these interactions. And that's when you get really, really complicated stuff. And this can get ridiculously complicated. That makes sense? Yep.
When you said combined S values, did you mean S
Spin.
or S like the script S?
Okay, so we're combining S values here. We mean the spin values here, but it is confusing because we have the S value.
L or two S.
Yeah, so this one here,
Yeah.
this S here is the S12.
Okay. Yeah.
So this is how the spins couple, this is how the overall angular momentum couple, and this is how the angular momentum and the spin. Okay. And probably, if you're in engineering, you're probably already, or maybe in chemistry as well, you're probably already come across this equation, probably quite a bit. It's just everywhere. I'm gonna go pay my credit card, and they asked me about this. I said, well, tell me about the spectroscopic notation in your credit account. I turned off the hyperfine split. Oh, that explains it. Yeah. Happy day.